Okay, so these are a collection of disparate and interesting phenomena. We want to understand what they are. Let's put together what it is that we know. We are trying to understand something that produces luminosities on the order of, say, 10 trillion solar luminosities, produces it in the form of a non-thermal continuum. We've seen a non-thermal continuum previously in the spectrum of pulsars. We saw a power law spectrum generated by synchrotron radiation from relativistic charged particles. That's going to be a likely suspect here. Collimated jets, we saw those too in our discussion of pulsars, so we wouldn't be surprised if they made magnetic fields made an appearance here. What about how big this object is? Is this a galaxy? Is this a cluster of galaxies? Well, the variability, as it did in the case of the black hole in Cygnus X1, sets, as usual, a limit on the size of an object. An object cannot vary over a time delta t if its size is much larger than c times delta t, because then the different parts of the object can't act in concert over those times. And so the size of an object is limited by about c times delta t, where delta t is the length of time over which it varies. But in this case, the object is moving relativistically. We have to be careful. The delta t in question is the delta t in the rest frame of the object. When we compare that to us, we have to take into account both that the object is moving, so there's relativistic time dilation factor gamma, and there's a Doppler effect. Later signals come to us from farther away, so there's another factor of 1 plus v over c. So let's get some numbers. If we imagine an object moving away from us at a recessional velocity of a third, remember that was moderate for a quasar, that's a z of a third, and if it varies over, say, we observe it to vary significantly in luminosity over a day, plug in the numbers, and that limits its size to 60 astronomical units. Now that's big compared to my backyard. But we are talking about something with a luminosity of 10 trillion suns squeezed into essentially the size of the solar system. What could drive that? Well, in the case of the sun, we went over chemical interactions and gravitational interactions, and we had to invoke nuclear forces. But we're out of forces. As far as I know, there are only 4 forces in nature. It turns out we get to go back to gravity, and it was a proposal back in 1964 by Yakov Zeldovich that accretion onto a supermassive black hole would be sufficient to power, he was talking about quasars, but we'll see that all of these phenomena are related. Can accretion onto a supermassive black hole explain all the different phenomena? There are some interesting calculations that we can do to see if this is a sensible explanation, and in the process, learn some astronomy. So, what is the calculation I want to do? Well, I want to bring in this sort of universal property called the Eddington limit. What is the Eddington limit? The Eddington limit is the following statement. If you have an object that is radiating and accreting matter, then its mass determines a limiting luminosity. If it's too luminous for a given mass, it won't accrete matter. Why? Because the pressure of radiation will basically blow the would-be accreted matter away. How do we put that into a calculation? Well, let's imagine that over here is our object, some massive thing, a black hole, a neutron star, I don't care. And over here at a distance r from it is an atom. And said atom is presumably going to fall onto the black hole or whatever it is, liberating gravitational energy, which it will, in collisions, convert to heat and radiate and so on. So, what is going on? Well, there's of course a force of gravity if this thing has mass m, and this thing, the atom, has mass m. Then there's a force between them, the force of gravity, given by g_m over r squared. We're good so far. I was claiming that the radiation emitted by this luminous object was applying a force to this atom. Why would radiation apply a force to the atom? Can we understand it? Well, let's try. So the way radiation, one way to think about it is that photons are flying off, or light beams are flying off this luminous object, and some of them will impinge upon this atom, and when they do, there's some probability that they will be scattered or absorbed. Let's imagine that they're absorbed. If the atom absorbs a photon of energy E, then the atom gets excited and to some higher electronic level or becomes ionized, but in absorbing an energy E, I claim, it is also kicked away. Why is it kicked away? Well, because the energy of a photon, E, is related to its momentum we saw by E equals pc. Basically, take the relation between energy and momentum for a massive particle and set m to 0, and you see that E is p times c for a photon. So when you absorb light energy E, you're also absorbing momentum of magnitude p, which is E over c. And if this is a photon that came from the luminous object, it's always momentum up, away from the gravitational well. So on average, the probability to capture a photon applies on average to the average atom a force. How do we do that? Well, a force is the rate of change of the momentum of an average atom. And so what we need to know is the rate, the probability per unit time that an atom will absorb this much momentum. How do we do that? Well, I'm going to start writing an expression for the force applied by radiation to this same atom. And we won't be surprised to know that this has to do with the flux of light energy. This is the amount of energy escaping at radius r in this direction per square meter or per unit area. Now, the only thing we need to understand, this is the flux of energy. Dividing by c, we get the flux of momentum, because for each photon, its energy is related to its momentum that way. And what's left to determine is how much of all this does the atom grasp, and that will give us a rate of change of the atom's momentum per unit time. The missing quantity is a quantity of unit with the units of area, which is essentially the effective area that the atom presents. So basically, if you throw a beam of photons at the atom, there's some probability that it will absorb one, and you can express this probability by saying it's as if I replaced the atom by a little disk of some area, and it absorbed all the photons that impinged on that disk. And that represents the probability that a given photon will interact with the atom. We call this effective area the cross-section. We measure it by basically throwing a beam of light at an atom and observing how much of the light, a collection of atoms, not an atom, but how much of the beam per atom has been scattered. And we call this thing a cross-section and denote it by sigma. So look, I have the force of gravity acting this way. I have the force of radiation acting that way. And if they are equal, then the average atom will hover, and if the force of radiation is bigger, then the star will blow its would-be accretion disk apart. And so this sets, if you know the mass of your atom, say a hydrogen atom, and if you know the cross-section for its interaction with light, you can find a limit on the luminosity beyond which the star will stop accreting. So let's tabulate our results so far. We had these two expressions for the force of gravity and the force of radiation. Setting them equal to each other, I observe the usual cancellations. When I set these equal to each other, I can see that the distance r is completely irrelevant, and I can see that the limiting luminosity, it's called the Eddington luminosity, for a given mass is given by 4 pi c times gmm divided by sigma. For a given massive object, if it produces a luminosity bigger than this, it won't accrete. So let's tabulate that. And what's left is to provide you with the data for m and sigma t. For m, I'll use the mass of a proton or the mass of a hydrogen atom. The value of sigma t, as I said, is measured. It's at the relevant energies. It's called the Thomson cross-section. And this is the effective area that an electron presents. The one electron of a hydrogen atom presents to the incoming radiation. I can plug this in and chug the numbers, and I find that the Eddington luminosity for an object of mass m scattering off hydrogen is scaled to the sun is given by this value. What that means is that an object with the solar mass will blow itself apart and stop accreting under radiation pressure if its luminosity is 32,000 times the luminosity of the sun. Our sun is clearly in no danger. Oh, good. But we are looking for a power source, accretion onto a black hole, that will produce a luminosity here of 10 trillion times the luminosity of the sun. How massive must our black hole be in order for that to be the case? For example, if I were to plug in here and obtain a value of 300 trillion times the mass of the sun, I would say I've never seen a black hole with that mass. This is the wrong mechanism. So we plug the numbers again, take 10 to the 13 divided by 32,000, and we find that our black hole must have a mass of about 300 million solar masses. This is big for a galactic black hole, but not out of range. We saw that galactic black holes range up in mass to a few billion solar masses. So these are the larger black holes in the center of galaxies would be sufficient, would be capable of emitting this much radiation without blowing apart their accretion disk. Would they fit in our 60 astronomical unit limit? Well, we have an expression for the Schwarzschild radius of a black hole, just to give you a sense of the size of the black hole. The Schwarzschild radius is approximately the mass divided by the solar mass times 3 kilometers or so. Plug the numbers in for this black hole with its mass of 310 million solar masses, and you find that its Schwarzschild radius is 6 astronomical units. Yes, sir, it fits very neatly into the size limitation we gave it. Okay, so now we have the ability, we meet the Eddington criterion with reasonable black holes, so we'll take this as our model, a black hole with a mass of 3,100 million solar masses, emitting 10 to the 13 solar luminosities. How does that work? How does a black hole get so luminous? Of course, we understand that what's emitting light is not actually the black hole. It is the accretion disk around the black hole. The power is obtained by the conversion of gravitational energy as matter falls in to heat and radiation in interaction within the accretion disk. Matter falls to where? Well, when it falls onto the black hole, then that's not a good place to extract radiation, because once it hits the Schwarzschild radius, you won't see it anymore, and the radiation will never escape. But let's imagine that all of the light is emitted, as we suggested, from about the innermost stable orbit at 3 Schwarzschild radii. Well, what's the gravitational energy of an object at 3 Schwarzschild radii? Well, we have an expression, a non-relativistic expression, for the total energy of an object orbiting at a distance r from another object. We've computed this and used it several times. And I can use my relation that says that Rs, the Schwarzschild radius, is 2gm over c squared, to replace gm here by Rs, and I see that what I have here, gm is Rsc squared over 2, so this is Rsmc squared over 4r. So at the Schwarzschild radius, by this non-relativistic calculation, you'd predict that your gravitational, your binding energy is of the order of about a quarter your rest mass. Now this turns out to be, and at 3 times, it would be about a 12th. This turns out to be a reasonable approximation, but non-relativistic calculations don't necessarily work very well at 3 times the Schwarzschild radius. A more careful relativistic calculation shows that the gravitational binding energy at 3 times the Schwarzschild radius is about 6% of your rest mass. So in the process of falling in, you have given up 6% of your rest mass to gravitational binding energy, which is available for conversion to other forms. In rotating black holes, you can do a little bit better. In rotating black holes, there's an outer horizon and an inner horizon, and the inner horizon, which is the innermost orbit, in the direction of the rotation of the black hole, and I'll explain why we think these black holes are rotating, as most black holes probably are, you can convert up to about 42% of your rest mass to gravitational, or your gravitational binding energy can be up to minus 0.42 of your rest energy, of your, rest mass, when you hit the inner horizon. So let's take an average of about, call eta the efficiency with which the black hole converts rest mass as its mass grows. It absorbs these objects and its rest mass grows. The mass of the black hole grows. How much stuff does the black hole needs to eat in order to produce a given luminosity? Well, assuming it converts mass to energy with an efficiency eta somewhere between these two values, we'll take 10% as a representative quantity. We need a rate of feeding for this black hole such that the efficiency times the rate at which it eats matter is equal to the luminosity, and we know our luminosity, 10 to the 13 solar luminosities, equates to eating matter at the rate of about 2.3 suns a year. Now, mark, I don't really mean eating suns. Black holes do not absorb stars. Stars orbit around black holes quite happily. Stars are not distributed objects. They don't experience much friction. They're concentrated mass. What I mean is a black hole needs to eat 2.3 solar masses of gas and dust, which are distributed and do suffer friction and do lose angular momentum and energy and convert it to heat as they fall. And so the accretion disk will not include stars, but it will include whatever gas and dust is around. And so as long as there is gas and dust around and the black hole is able to consume at this rate, it will be able to produce the luminosities observed. So the energy source for all of this is infalling matter. Okay, we've addressed one issue. Can the black hole produce the energy? Yes, as long as there's gas and dust. Maybe this is the criterion for what a quasar event is. A quasar event occurs when there is in the vicinity of the galactic black hole sufficient quantities of gas and dust that it can then accrete, and when the gas and dust is depleted, then the quasar event stops, and that's why it lasts on the orders of hundreds of millions of years. So far, so good. There's a missing ingredient. Jets, as we know, are driven by magnetic fields. I carefully explained that a black hole is characterized by mass, angular momentum, and charge. And in particular, I said it cannot have an independent magnetic field. So what's with this magnetic field, Ronan? Well, no, the black hole can't have a magnetic field, but the disk of heated, ionized plasma of charged particles rotating around a black hole surely can and will generate a magnetic field. That's one factor, but it turns out that there is a way for a black hole that is rotating. We didn't discuss rotating black holes, they're complicated, but a black hole that is rotating in an ambient magnetic field, in fact, will amplify the field, and the source of the energy for amplifying the field will be in effect be slowing down the rotation of a black hole. It's a complicated calculation, we won't do it, but in fact, yes, you can tap the rotational energy of the black hole to amplify the field created initially by the charged particles in the disk. So we can have magnetic fields and jets. So we're in a situation we recognize, and let's turn to how astronomers put all of this information together and develop a grand unified model of active galactic nuclei. So at the level of orders of magnitude, a black hole with a typical mass of a large galactic black hole can produce the energy output, but can it produce this whole wealth of phenomena that we described? That's the point of this unified model of active galactic nuclei. The answer is to a certain extent yes. The model is still being developed, and many of the details are too complicated for us to address, but some of the ways that it works are cool and accessible to us, and I wanted to share them with you. So what is the idea? The idea, here's our model. At the center sits our 300 million solar mass black hole. It's surrounded by an accretion disk. In the interior of the accretion disk, the gas is very hot. It is heated by the processes that we discussed. Infalling matter exchanges energy through friction, becomes very hot. Temperatures at the interior of the accretion disk can reach 700,000 Kelvin. The thermal pressure then inflates this to this donut-shaped radiation torus. And it is from here that the broad thermal aspect of the continuum radiation is emitted. Note there was a non-thermal component which comes from synchrotron radiation. We'll talk about that in a second. Interacting with the accretion disk, we have a magnetic field which powers, as we are familiar, polar jets. And these polar jets are very tightly collimated. When they plow into, they produce synchrotron radiation at all the way up into probably X-rays. The even harder X-rays are probably generated by a process called Compton scattering, in which a photon scattering off a high-energy particle is scattered backwards with a higher energy than the incoming photon. And so what this means is that if the orientation of the system is such that Earth sits over here, and we're viewing the galaxy pole on, so to speak, from the point of view of one of its poles, then the jet is aimed right at us. What we see is mainly the continuum radiation produced by the jet. This obscures everything that lies behind it, and because the jet is aimed at us, we will typically see superluminal motion in these cases. So if the orientation is this way, we observe what we call the blazar, very few spectral lines, superluminal motion, and a jet. Now, in other active galactic nuclei, that means if we're viewing it from a different direction, then we see some of the internal radiation from the disk. This contributes the thermal component. We see some of the radiation produced in the jet as charged particles ionize gas particles, and the broadened line emission is supposedly originates from clouds of gas orbiting right outside. It turns out that it's not a uniform distribution. It's important that it clumps in clouds for reasons that I won't explain because I don't completely understand them. Right outside the radiation torus, and we can estimate how far they are because we have a way. We know the speed, about 5,000 kilometers per second, say, and if we know the speed with which something is orbiting, then our good old friend Newton tells us how to make a calculation of its speed. Remember that we have v squared over r. The centripetal acceleration is supposed to be gm over r squared. So again, v squared is gm over r. I'll use again my old trick of replacing gm by, I still have to write it out, rs is 2gm over c squared, which means that gm is rs times c squared over 2r. What that tells me is that if I want to know the distance at which something is orbiting, I can solve this equation for r as rs times c squared over 2v squared. Well, I know the v. I can figure out how many Schwarzschild radii away from the black hole this matter is orbiting. If it's orbiting at 5,000 kilometers per second, plug in the numbers, and you find that the broadened emission lines are for matter that is ionized by the high-energy radiation from the radiation torus and is orbiting a distance of a few thousand Schwarzschild radii. Remember that our Schwarzschild radius was a few AU, so this is a few thousand AU, maybe 10,000 AU, still very close to the center of this whole model. And then outside the radiation torus and this inner cloud of gas clouds, inner orbits of gas clouds that are emitting the broadened line emission, we have the rest of the accretion disk, and it is surrounded by a dense torus of cooler, maybe 10,000 Kelvin, opaque gas. And the idea is that if we are viewing the system edge-on, then this torus of opaque gas absorbs both the X-rays and the broadened line emission from these clouds in the interior. What we do see is radiation coming from farther out. So farther out, and again, if you compute, by the way, the distance, a few thousand Schwarzschild radii, and measure that in light time, you will see that a few months of light travel is reasonable for the distance from the torus to these broadened line spectrum clouds, which is the lag that we saw in the way that intensity responds when this flares up because some large chunk of matter fell into the black hole. This gets heated, the emission, continuum emission increases, and then a few weeks later, that increased light output arrives and ionizes the broad emission line clouds, and the broadened line emission increases correspondingly. Outside this opaque torus orbit at larger distances further clouds of matter. Again, we need it to be clumped, and this is where the velocities are slower, that we are farther from the black hole, and at these distances, a few tens of thousands or 100,000 Schwarzschild radii orbit more gas clouds. This is where the narrow line spectrum is produced. If you are viewing the system edge-on, the region where the broad line spectrum is produced is obscured from you. What you will see is the narrow line spectrum along with some of the continuum, which is reflected by scattered off various of these items. You'll see less luminosity, and you will see Seifert type 2, or a narrow line radio galaxy. Whereas if you are viewing the system at an angle, you will have a view both of the broadened lines and of the continuum, and of the narrow lines, and you will be viewing a type 1 Seyfert galaxy if it's a spiral, or a wide, broad line radio galaxy, or a quasar. And so, in some sense, the orientation of the system relative to our line of sight and the interior structure allow one unified model to describe all these disparate phenomena, and I think that was a very cool story. I hope that you found it worth the time.